in a few admin things. Um, I have been made aware that some of you are from CSC 209. Sorry, I'll adjust my audio. Oh God. Is it better? I'll just adjust my mic towards me. Okay, great. So, I have been made aware that some of you are from CSC 209. I just want to make it clear for obvious reasons that I cannot offer any help with the upcoming assignment on CSC 209. That being said, I wish all of you the best, and I hope you do well. So another thing is if you want to code along, um, I did mention this earlier, but you can SSH into the DH 2020 lab machines using VS Code as the remote SSH extension. So in order to get the code, you have to open the terminal with control and then backtick in VS Code. Open the terminal tab and run this command git clone and this URL. This is the GitHub repository that contains all of the C code that we will be covering today. So I'll show you what that should look like. All right, so it should look like this. There will be a if you press control tick, it should open the terminal, and then you can start running commands like that. Okay, so this is the code we'll be going over later. Now with that out of the way, let's continue. So what is C? C is a statically typed compiled programming language. So unlike an interpreted programming language like Python, C is in an interpreted programming language like Python, a program takes your code and actually runs your code for you. It is reading your code, understanding what it does, and then executing that code on your behalf. What a compiled programming language does is it takes your code and converts that code into an executable application that you can run on your system. So C is one of the oldest programming languages still in widespread use. It was developed by Ken Thompson and Dennis Ritchie at Bell Labs for the Unix operating system. And descendants of Unix include Mac OS and Linux, and all of which are still written in C. So why learn C? C has had a massive impact on today's society in computer science. It is the implementation of numerous software tools. Almost all modern operating systems are written in C, or at least some part of them are written in C. Linux, Windows, Mac OS are all written in C to at least some extent. Windows does include some C++. The Python interpreter is written entirely in C. The Java virtual machine that runs your compiled Java bytecode is also written in C. And honestly, anything low level that runs very close to the metal, very close to the hardware, anything that you can think of, chances are it is written in C. So another thing is that the syntax of C has influenced numerous other programming languages. So this image here is a screenshot from the Wikipedia page of C, and this blue link here is literally a dedicated Wikipedia page that lists every single programming language that C has influenced. So it's a lot. And if you look at languages, if you've taken 207, you've probably learned Java. You'll definitely see the similarities. If you've coded in JavaScript, you will also definitely see the similarities. So now I know a lot of you are coming from a Python background. So I guess it would be apt for me to draw some similarities and draw some comparisons between Python and C. Python is interpreted, as I said earlier, and C is compiled. Python is dynamically typed, and C is statically typed. So dynamic typing is when variables are assigned types when they are run, and the types of these variables can change throughout the runtime of the program. However, in C, you declare the type of a variable when you declare it, and it does not change. So strong and weak typing are somewhat influenced by these. They don't have very well defined characteristics, but generally speaking, a strong type system is one that defines a set a set of operations that you can do on a type and will not allow you to do anything beyond those operations. Whereas with a weak type system, you can do whatever you want and the compiler will just let you. It's a little bit more dangerous, so you need to, and programming in such a language does require you to have a good idea of what you are, of the types of the variables you're working with. So next, Python is object oriented. Um, if you've taken 148 or even 108, you will know this. Um, C, on the other hand, is structural or imperative. That means C has nothing that resembles object-oriented programming. It has no inheritance, it has no polymorphism. In fact, it is a very, very bare bones language. It's literally the bare basics you need to write any program, plus a few other things to make your life easier, and that's it. Python is easy to use and very beginner friendly. C, on the other hand, is easy to learn, but it's very difficult to master. Of course, downside of this, of Python being easy to use, is that it is very, very slow. And on the other hand, C is extremely, extremely fast. If you were to program some sort of computationally intensive function in Python and an equivalent program in C, and you run the two of them, you will see that the Python program takes infinitely longer than C. On the other hand, um, C is, of course, a lot more difficult to program in. There are a lot more things you need to keep track of. So, there are upsides and downsides to everything. So, with all of that out of the way, let's actually look at some C code now. So this is the basic annotation, the basic structure of a C program. As you can see at the top, we have import statements at the top. So these are basic import libraries. Then we have, and this is a basic function in C. As you can see, you declare the return type, the parameters taken, and this is the function to print, and this is the return value of the function. So in C, the entry point to a program is always denoted main. It's a bit like if name equals underscore underscore main in Python. That's when the C compiler will actually look out for that main function, and it will designate that as the entry point to the program. And the entire execution of the program will actually start from that main function. So let's go over what do you get in C. In C, you have the basic programming constructs. You have conditional statements plus another one called switch statement. You have the basic loops, for and while loops. You have function calls and typecasting. You also have that in Python, but C is a lot more permissive about how you convert types. Of course, in data types, you have various flavors of integers. This is because in Python, you just have the one integer. I cannot delve into why that's the case, but in C, you have various types of integers. You have integers, you have unsigned integers, you have long integers, you have long integers. These are all various types of integers that you can use. You have floats and doubles. You should know what those are. Decimal point numbers. You have characters, which are actually separate from strings. So characters are just individual characters, and they take up 1 byte. And then you have booleans with a caveat. I'll cover that later. You have arrays, or in Python you know them as lists. And these are actually much more different from Python lists, and you'll see why later. You have structs. These are the closest thing you'll get to classes in C. They allow you to create your own clustered data, create your own types. You have pointers. Those are a very important aspect of C, which we will go very into depth later. And what about strings? So if you coded in Python, you're very, very used to dealing with strings as just another object. We will see that why that's not technically the case in C. So moving on to point. So C is a very, very simple language, but it's very hard to master. You need to keep track of a lot of things. There are a lot of things. Yeah, basically, you need to keep track of a lot of things. So let's talk about pointers. So it's before we actually get into what pointers are, I think we should start with sorry, hold on. Before that, let's look at some basic syntax. So this is the example code. It's examples.c in your in the repository. If you cloned it, you should be able to look at it yourself. Can everyone see my screen? I assume you guys can. Okay, awesome. So these are the basic import statements. You have standard IO, you have the standard library, you have strings, and this is why I said Booleans are not technically a type, because they're not built into the language. They are actually defined by another library within C. And then of course you have math functions, same as Python. So this is the entry point to our function. Right now it just prints hello world. You can ignore the format here. That's just my my IDE trying to make my life easier for me. So you'll notice that I have these function prototypes up here. What void means, it means that the function doesn't return anything. It's equivalent to a function returning none in Python. So in this case, main returns an integer. Main actually returns this integer to the operating system to tell the operating system the exit status of the program. So if it returns a 0, it means the program executed correctly. If it returns a 1 or anything other than 0, it tells the operating system that the program exited with an error. So the void here just means that the function doesn't take any arguments. And these functions up here are what we call function prototypes. These are because we cannot actually call functions defined lower down in the file and just call them in a higher function. You actually have to declare them up here first, and then you can actually call them further down. This is because C is a very old language. It's just a remnant of how C was implemented back then. When memory was tight, execution was tight, so you had to do a lot of workarounds and hacks just to make things work. So moving on to basic control flow. If you've done JavaScript, you've done Java, these will look very, very familiar to you. So unlike Python, where else if is just one word, elif, we have two words for it, else if. Very, very simple. This is also where you declare function parameters. So this function takes an integer I, it compares I, etc., etc. Then we have switches. So same thing, this function takes an integer I, and then it compares I to, say, if it's case 1, it does this. This break statement here tells the compiler that you want, if this case gets executed, you want to jump out of the statement and continue executing. Because if you don't put this break statement here, we actually move on to the next case. So this break statement is actually very, very important. And if none of the cases meet, it will just execute the default case. Very, very simple. This is an example of a loop. Again, ignore this. These white numbers in brackets. This is just my IDE trying to make my life easier. This is how we declare an array. In C, you declare the type of the array, and then you indicate that it's an array with the brackets here. You can also declare its size, like so. You don't have to, but you can. Then you have a curly brackets here, and then you just declare the contents of the array. So now how these differ from lists in Python is that arrays only accept one single type. That means every member in the array has to be of the same type. This is because of memory, and this is because the compiler needs to know if you want to access a certain member in the array, it needs to know where in memory to jump to. Okay, if all the types of the members are different, it doesn't know how it's going to make that jump. So every member has to be the same, so it can easily calculate the offset. And this actually will link into pointers and why they are so important. This is a for loop. If you've coded JavaScript or Java, this will be child's play to you. You declare an integer, a condition, and then something else to do. So this plus plus here, for those who haven't coded in something like Java or JavaScript, this means to increment. In Python, this is the same as plus equals 1, sorry. Then you just access the current member of the array you are at. We are iterating over this array here. And then you just do something with it. So, and for those of you who have worked with Java, unfortunately, there's no such thing as a for each loop in C. It just does not work. Then of course we have while loops. This is a terminating while loop. So for every iteration of the loop, I decrements, and once it hits 0, the loop terminates. Then we have an infinite loop. So while 1, because 1 is a truthy value, so it always evaluates to true. So falsy values include null pointers, which we'll get to, and 0 in C. So since this always evaluates to true, it'll just keep looping and looping forever and ever and ever until it hits a break statement or something like that. Then we have typecasting. So it's equivalent to calling int on some value. Same thing here. You declare a character A, and then you can cast it to an integer by putting this here in parentheses, and then int that will cast it to an integer, and then you can even further cast it to a float, and you can even cast integers to pointers. So this is a null pointer. It points to memory address 0. So this asterisk here indicates a pointer. We'll cover that later. Don't worry. This is actually how null is implemented in C, which we will again cover later. Right, so back to the slides. Pointers are a motivating example because, so how many bytes do data types use, right? So in Python, you didn't really have to worry about this, but that's because it's interpreted, right? So you have a program you actually have an underlying program beneath all your Python code that is actually handling all your memory accesses for you. So, but in C, you don't have that, right? You have a compiler that just converts it into an executable, and that's it. The executable has to do everything on its own. So how many bytes do data types use? So first we have the integers. By default, if you use a standard int, that's 4 bytes, 32 bits. Longs are 8 bytes, 64 bits. That's why they're called longs, because they're double the length. They can store larger numbers. Then you have characters. Characters are always 1 byte, at least in ASCII. Unicode is a whole different story. If you want to read about that, that's out of the scope of this workshop. Then we have booleans. They're always 1 byte. They're always either 1 or 0. Then we have arrays. They are however big the programmer declares them to be. So if you saw in the code that we declare an array here, the compiler at compile time, it knows how big this array is. It's 5 integers long, right? You cannot change it. That's another difference that Python lists have from C arrays. Python lists are dynamically sized. They can change. Their size can change. C arrays cannot. At least those that are declared in the source code. So even though they are arbitrarily big, their size is always known at compile time. So the compiler knows how to work with that information. So now you notice that there's one very, very fundamental data type missing. How big is a string? So, I mean, we can determine how big a string is by counting how many characters is in it, right? So the string hello world has 12 characters, so it has 12 bytes. The string I like Danzigaro's cows has 25 characters, so it has 25 bytes. So we see that strings can vary in their length, in their size. A string can be 1 byte, hundreds of bytes long, thousands of bytes long. We don't know how big a string is. Or rather, strings have an arbitrary size that we don't always know at compile time. So the compiler doesn't necessarily know how to work with that information, right? So let's say you have a string that's hard-coded in the program. Obviously, the compiler will know how big that string is. But if, let's say, we're asking the user to enter in some input, we don't know how long that string is going to be. So we don't know how much memory we're going to set aside for it. And this is where pointers come in. So a pointer is just another number. That's the first thing that you should know. But instead of storing the value of an object, it stores the memory address of an object. So that's why it's called a pointer. It points to the object, right? So an object lives in memory somewhere. It has to live in memory somewhere, right? So that location is always assigned an object, is assigned an address, right? So think about your house address. It's not your actual house, but it tells you how to get to your house, right? It tells anyone how to get to your house. So it points. So you can think of an address as a pointer to your house. You learned about about object IDs in Python in CSE 148. It's basically the same thing. And how multiple variables can have the same ID because they're pointing to the same object. That's exactly what Python is. And that's the reason why Python works, is because everything in Python is a pointer to an object in memory. And the Python interpreter is actually managing that memory for you. So, and pointers we always know how big pointers are. That's why they're so important. They are either 4 bytes or 8 bytes. 4 bytes on a 32-bit system, and 8 bytes or 64 bits on a 64-bit system. So they are indicated, as we saw earlier, by an asterisk in C. So for example, int star C declares a pointer that points to an integer. So it's not actually storing the value of the integer, it's storing the memory address of where that integer lives. Okay? And then, of course, we need some way to operate on pointers. So the pointer operators are an ampersand, which is the reference operator, and another asterisk, the dereference operator. This is actually what tripped me up when I first learned pointers for the first time, is because the type declaration and a pointer operator are the exact same character. So it does take a while to work it out, but it does come with practice. So what the reference operator does is it basically tells the compiler to give me the memory address of an object. So let's say we have a variable called integer. We have an integer variable, right? If you put an ampersand before the variable name, it's basically telling the compiler, hey, give me a pointer to that integer. Don't give me the value of that integer. Give me a pointer to that integer. And then we use the dereference operator on a pointer. So let's say we already have a pointer, and we say, okay, I want to follow this pointer and see what the value of the object is that's living at that address. That's what the asterisk does. It dereferences the pointer and takes us to the object. And this brings me to my final point. And this is how strings are stored in C. Strings don't have their separate type in C. They are stored as pointers to a character, or an array of characters, or a list of characters, if you want to put it that way. Yeah. So if you're wondering how exactly do lists if strings are an array, how exactly do we tell when strings end? So we use something that's called a null byte. So a null byte is just a byte that's set to 0, like this. So we have a variable called string. It is type character pointer. So this is the character. This is the variable type. It's a pointer to a character called string, and it points to this array in memory. These are the memory addresses of each character, and this is the null byte. In C, it's usually denoted as a \0, and this is a byte where all its bits are set to 0. So if we are iterating along a string, so this is not 0, this is not 0, this is not 0, and so on and so forth, until we hit something that is 0, we know that we've hit the end of our string. So that is actually how operating on strings works. Please note that this is unique to strings only. For other arrays, let's say you're working with an array of integers, you're working with an array of struct pointers, you have to always bear in mind how long or how large that array is. You don't know for sure, which is why it is so important. Memory management in C is so important, and that is why C is such a difficult language to learn. All right, so now let's talk about how we're actually going to be working with memory in C. So we're going to cover C's memory model. But before that, we'll take a look at some code that works with pointers. So here, if you go back to examples.c, if you're following along, go to section 2, where we have pointers and memory management. So this is the wrong way to swap two numbers. If you were to pass in x and y, declare x and y, pass in x and y, you'll see that they don't get swapped properly. And this is because the values actually get copied in, so the original integers don't actually change. These get changed, but the others don't get changed. So what you want to do is to pass in a pointer to those two integers. And what you do is you declare an integer, and then you actually dereference that pointer. So you copy, you take x, you follow that pointer to wherever x is pointing, you take that value and you copy it into temp, right? Then you take you dereference x, right? You follow x where x is pointing, you take that value, right? You and then you copy it into where y is pointing. So you've essentially moved the value of x into y, and you have the value of x being stored in a temporary variable. Then you figure out where y is pointing, and then you move that value into y. Into y. And so that carries out the swap. And I'll show you. I have actually a driver function down here that actually does the swap. Yeah. And I will call it for you guys now, and you'll see how that works. So one more thing, I'll show you why we need function prototypes. If I don't put the function prototype up there, my IDE will complain. It will say undeclared function, blah blah blah. So what we need to do is we do need to have a do swap function here. So now, this is how you run a C program, at least on the lab machines. In an IDE like CLion or NetBeans, if you still use that, it's going to be different. But this is how you run it in a text editor like VS Code or on the shell. So if you open up the terminal, we run a program called GCC. GCC is the C compiler on all Unix machines. We do output examples, examples.c. We run it. That will create a new file called examples. This is an executable file, so we can run it with /examples. And you'll see that after the swap, the numbers have been swapped correctly. I think you can easily reason for yourself why this is wrong and why this is correct. All right, back to the slides. So C's memory model is actually divided into two main parts. Actually, wait, before that, I should check if you have any questions. Booleans are 1 byte, yes. Yes, that's the null terminate character is included in the string length. That's I forgot to mention that. So if you a string of 5 characters actually has 6 characters in it. So you do have to account for that. But if you call a function like strlen, which it will return 5. It doesn't count the null terminator. No, ints are not 1 byte. Ints are 4 bytes. It's represented by a char, 0 or 1. So it's 7, but it's actually 6. If you call a string length function, it will return 6 instead of 7 because you don't account it, because string length doesn't take into account the null terminator. But if you're allocating memory for a string, you need to account for it. So you always need to +1. Is it possible to swap ins? Well, no. Yes, it's not possible to swap ins without pointers, but not because they are immutable. This is not Python. In C, there is no such thing as mutability or immutability. Everything is mutable in C. But what you're doing is but now you need to actually account for memory, right? Where that object lives in memory. In Python, that it accounts for that for you. But in C, it doesn't do that. So you need to actually dereference, copy out, copy back in, and so on and so forth. Does that make sense? All right, thank you. Awesome. Let's go back. So we have 2 areas of memory in a C program. The stack and the heap. So the stack is, you learned it in Python as the call stack. It's actually where functions get called and so on and so forth. Variables, most size variables will live there. Integers, pointers, predefined arrays. Most items get allocated and deallocated automatically when a function returns. This is as a result of the architecture, the computer architecture that C is running on. It's not within the scope of this workshop. The size of stack variables cannot be changed. This is very, very important. And that is why we have the heap. The heap is used for storing variables of an unknown size. So strings, we covered that. Or even dynamic arrays. That's actually how that is actually how lists are implemented in Python. A list is just a pointer to an area of memory that is managed automatically by the Python interpreter. The size of heap variables can be changed through calling a function. I will show you that later. And the heap is always interacted with through pointers. Always, always, always. You will never find a time where you actually interact with the heap directly. It's always, always, always through pointers. And the heap must be managed manually by the programmer. There is no way around it. Python has a garbage collector, that's what it's called, that manages memory for you. C does not. You have to manage it yourself. And that is why memory management is so, so, so important in C. In fact, there are whole strategies that people have worked up for dealing with this problem. Programs like C, C++, Rust, the whole languages have been built on some wild idea someone had on how to properly manage memory. That's how important memory management is. But because C is so primitive, C is so low level, you do it yourself, unfortunately. So, how do we manage memory? Memory management is done with two main functions, malloc and free. As you can tell, malloc allocates memory, free frees the memory. So, malloc allocates a block of memory on the heap and it returns a pointer to the allocated block. Okay, it takes an argument specifying how many bytes the programmer wants, and it comes in various flavors. Calloc, it actually zeroes out the memory. So, when you call memory, that memory may have been used by something else, right? So it may still have that old data still in that, right? So what calloc does is it just zeroes out. It sets all the bytes in the block to 0. Generally speaking, you don't want to do that because that takes time. It's an ON operation, depending on how many bytes you've given to calloc. But malloc, it's usually constant time. Realloc resizes an existing block of memory. Realloc, it takes an existing pointer. That pointer has to be allocated by malloc. By the way, this is not enforced. This is a contract, right? So if you violate that contract, bad things will happen. So, and again, this is why memory management and keeping track of everything is so important in C, because C just gives you all the tools and no guardrails. So reallocates an existing already allocated block of memory. You can shrink it, you can grow it, however you want. If memory allocation fails for whatever reason, malloc returns a null pointer. So a null pointer is a pointer whose value is set to 0. So it's pointing to memory address 0. So in most systems, memory address 0 is always an invalid address. So if you follow a pointer and see that it points to 0, you know that something has gone wrong. That's often how you actually diagnose errors in C, by returning some sort of integer or null pointer, because C has no try catch or try except. Like I said, primitive, you gotta do everything yourself. Free deallocates the memory being pointed to by a given pointer and frees it up for other use. Takes one argument, it takes a pointer, any pointer that points to the block of memory to be deallocated. Again, the block to be deallocated must have been previously allocated. If not, bad things happen. What exactly? No one knows for sure. It's called undefined behavior. There's a whole Wikipedia article about it. I don't have time to get into it today, but that's essentially what it does. So, memory management best practices. The golden rule of memory management is anything allocated must always be free. For every malloc, there must exist one and only one free. If you malloc one pointer, you free that pointer, you free it again, bad things will happen. Do not do that. Avoid aliasing. So in Python, you can have a situation where two variables point to the same object. You can have the same thing where two pointers point to the same memory address. That's not a great thing. It's not a bad thing, but it's also not great. Try to avoid it. Dangling pointers that point to undefined places. Any dangling pointer should always be set to a null pointer. That's how you tell if a pointer is valid or invalid. And watch out for out of bounds errors. Always account for what memory you're using. So What can go wrong if you violate any of these rules? Segfaults. It's when your program does an unauthorized memory access, the operating system catches it, and it terminates your program. That's actually a good thing, because you don't want it to continue executing and do weird shit. Use after free. You free twice. And this is why I say to avoid aliasing, because aliasing, you will usually, okay, not usually, but will more often than not result in some sort of programming error that results in a double free. You do not want that. Buffer overflows. You read in more data, or you write more data than has been allocated. Always keep track of how much memory you're using. This is why, and all these are actually security vulnerabilities. This is why keeping track of memory is so important. Great, let's check what you've been asked. So I'm not going to talk about safe and unsafe functions. That's more of a Rust. That's more of a Rust thing. So char c equals hello, that will be stored in the stack. Yes, correct. It's stored in the stack. If anything's allocated from malloc, it's a heap. If it's not malloced, it is stacked. It's a stack variable. ICPR is right. It is stored in read-only memory, but so the literal string hello gets stored in the final executable, and then C is just a pointer to that memory address. Yes, and again, yes, you cannot mutate that string for any reason. Malloc zeroes out memory. It can make null, because if allocation fails, it will return null. But it's just another flavor of malloc that zeroes out the memory before it returns the pointer. Okay, moving on to some code. So this is stack versus heap. This is where we allocate a stack string. So we allocate an array, a character array of 32 characters. We read in a string, and then we print it out. Okay, and then we have this is a heap string, where we actually allocate a block of 32 bytes, and then of course we have to free it afterwards. So this is why we have the heap, because the heap allows us to dynamically resize. So if we read in a string that's more than 32 characters long, we are able, if we have some mechanism to detect that, we can easily call realloc and allocate a bigger block of memory that we can then read more data into. You can't do that with a stack variable, because, like I said, stack variables cannot change size. And then this is an example of aliasing. So we allocate some integer. We allocate 4 bytes. Size of returns 4 for integer. We set the value of that memory address to 16. Then we have another pointer that points to that block of memory, and then we free x. So x is now a dangling pointer, and we set x to null. Good memory management. But we still have an integer pointer called y. It's now pointing to memory that has already been freed. So what happens if we call free y? Bad things happen. You do not want that, right? That's why I say try to avoid aliasing, because it just leads to bad things. Okay, we're running very low on time, but I think I can make this work. Structs and typedefs. Structs, if you've learned classes, you will know structs. Structs allow you to create custom data types, and they provide ways of grouping related data under a single name. Same thing with classes. Typedefs allow you to create a type alias. You can use it to redefine existing types, or define a struct to use more succinct syntax. And surprise, pointers are always used as structs, because C is a pass-by value language. So whenever a function is called and you pass in a parameter, you always the value of that parameter actually gets copied into the new stack frame. So whatever, you have a massive struct, that are you going to copy the entire struct in? Of course not. You copy in a pointer to that struct. So that function can just follow that pointer and access the data it needs. So pointers essentially allow you to do pass by reference. So common in syntax will include declaring a struct. You always declare a struct with struct, the name of the struct, and a pointer to that struct. So this is now a struct pointer with a variable name. You can typedef a pointer to a struct as a new type, then use that type in your variable declaration. And since this is of a type pointer, so you don't have to include the asterisk here. And then you can call malloc. Size of calculates the number of bytes needed and automatically does it for you. All right. So before we put it all together, I'll show you some examples. Before that, yes, I can link the slides definitely. Do you need to cast? You don't. The compiler implicitly casts for you. Yep, Daniel got it right. Yes, malloc returns void. A void pointer is just a pointer of any type. It gets automatically coerced into the type that the variable is declared. The compiler will know this because all the types of all variables are declared at compile time. All right, so let's look at some code. This is a struct. I declared a struct. You declare its fields, type, field name, type, field name. Then you can typedef a struct. So typedef usually allows you to avoid typing struct name all this whole time. So now you can just type new struct. You can even typedef existing types. That's how you can get string from char pointer. It's a bit easier to work with. Just remember that string is a pointer and not an actual type, because the asterisk will actually clue you in to whether something's a pointer or not. If you typedef something that's no longer a pointer, that's bad. So this is a struct demo. We can call size of to tell you how big our struct is. We can declare a string with our new typedef. We declare a struct on the stack. So this declares a struct on the stack. We fill in its fields. We can print fields, and then we can declare a struct on the heap. So this we can call malloc, and then returns a pointer. Remember, malloc returns null if something goes wrong. So you always want to check if your pointer is null. Then you can dereference a struct. This is actually very important syntax. You want to dereference the struct first in parentheses. Then you can use the dot operator to access its fields. Now, because it's such a common operation in C, they actually introduced a shortcut. You can just type an arrow. So this is a struct pointer. This is just a dash and a caret like that. Same. And then this allows you to just directly access. It is basically dereference the struct and then dereferences to the field that you want. And then of course we need to free our struct at the end. So now, how do you check if your program is using more memory than you accounted for? There's a program called Valgrind. It's called Valgrind like this. It does exist on the lab computer, so you can run this no problem. It will actually check how many accesses, how many allocations, and how many frees your program does, and it will check that they match. So I created struct demo. Let's call that. We better call it. And then I'm gonna recompile it, and then I can call it. So now we can see that we can print out size of will calculate the size of the struct for us. My system is a 64-bit system, so a pointer is 8 bytes. It's a bit strange. Okay. Because it's padded. It's not padded, right? So it does some aligning with the bytes. You don't need to know what it does. But you just need to know that size of allows you to just, instead of physically calculating the size, it just allows you to return the value directly. It just makes your life easier. So now we can use Valgrind to check how many how our program did. And you can see that all key blocks are free, no leaks possible, 2 allocs, 2 frees. These two numbers must always match. Okay, any questions? Nope, no questions. Awesome. So now let's put it all together. We're going to implement a linked list. If you've done CSC 148, you'll know exactly what that is. So we will implement append, push, remove. I forgot to put pop. And we will also implement index, which is basically get item in Python. So this is the code. It's all linked here. First, so we declare our functions and our types in what's called a header file. Also, if you guys don't have time, you guys can leave if you want. I'm so sorry we didn't get to finish on time, but if you want to stay, you're more than welcome to. So first we declare our types. So this should look very familiar to you. We have a linked list type and we have a node. Each node stores a value and it points to the next node in the list. So each node has a value and a pointer to the next node. So notice that we have a pointer to another struct called next, and node stores the value. I saw someone typing just now. It cannot set elements to null because everything in C is just bytes. So it's just how you want to interpret those bytes. So if you want to interpret those bytes as a pointer, it's a null pointer. That's really all it is. I really don't have time to get into it now. So first, of course, we declare our linked list. We have a variable to track our field to track our length, and we have a pointer to the first node in the list. If you have access to the code, you guys can easily look through it. So these are our function prototypes. You always declare them in a header file. So we have a function to create, to destroy, a linked list. So this is equivalent to malloc and free. We have a push, append, pop, remove, index, and print. Self-explanatory. Then this is where the functions get implemented in a .c file. So header files are .h, c files are .c. So I'm not going to go over the business logic. It should be pretty self-explanatory if you read the code. I'll just point out that every time we push, we are allocating memory for a new node. Then we are doing some, checking. We are initializing the node, right? So we're setting the values in the node, and then we put it somewhere in the list, and then we increment the length. That's what push does. Then we have, and you notice that all these functions return an integer, so that tells you how it went. So if it's null, you return 0. Self-explanatory. That tells us that we have an error condition. Then we have append. It just does the same thing, but push puts it to the front, append puts it at the back. So we have a loop that iterates to the end. Self-explanatory. Again, malloc. Then we have pop. Pop frees the list, frees the node that we want to remove. It just removes the head and moves everything down by 1. Removes it at a certain index. Again, free. So you notice that for every malloc we have one free, right? That's a common theme that you will see. We have index. It returns a pointer to an integer, and not an integer itself. Because if we want to check that if we have an out of bounds error, we want to return null. Again, that's actually how we detect for errors. Let's check we have condition. No questions. Awesome. And then again, you see this here, the ampersand, or the give me the address. Give me the address operator that returns as a pointer. Then we have print that just prints out the list. Self-explanatory. All right, so I have some driver code here that actually runs the linked list program for us. There's a problem with this code. We'll see if we can spot it later. But we can compile this code with gcc linked list. So you need to include all the files that you want to compile. Again, remember, you see main here. That means that's our entry point. Self-explanatory. I will compile it. It compiles with no problems. We run it. Again, nothing out of the ordinary. So you can actually trace it. We declare a list as an empty list. We set the list as hidden null to avoid dangling pointers. We test printing on an empty list. So remember, print, all these functions take a pointer to a list. So you want to pass in the reference to the list, not the list itself. We try printing on an empty list. It just prints out end. It works. Populate the list. We populate it. I have a populate list function down here that just runs a for loop, pushes items, and appends items. So it looks correct, right? 5, 4, 3, 2, 1, and then 6 and 7 at the end. Then we print it again. That's what that does. We try removing an item. It works. It all works correctly. It pops from the list. That's correct. We try out of bounds indexing. Everything gets handled correctly. And we try to print the list at the end. Everything looks correct. It returns correctly, right? But there is an invisible bug here. Can someone tell me what it is? I will check again later, but you guys can look at the code. There is an invisible bug here. Even though the code runs correctly, everything works out fine, there is an invisible bug in this program. Can anyone tell me what it is? Yep, you're right, some memory leak, but what is it? I did not free the list at the end. That's correct. But again, that's not the exact problem I'm looking for. Right? We declared the list on the stack. The list is a stack variable. So we don't need to free the list. But what do we need to free? There are things that we need to free. Yeah, free what I mallocked, but what did I malloc that I'm not freeing? It's the key is here. Nodes, correct. I mallocked nodes, but I did not free them. And you will actually see this when I run Valgrind on it. You'll see that it leaks. It takes a while. Oh, okay. Didn't take that while. It didn't take. See, I locked 8 times. I only freed 3 times. So it will tell me how much I leaked, how much I lost, and whatever. Right? So we need to obviously we need to fix this by freeing it, right? And it just so happens that I have a linked list destroy function that I have already implemented. It just iterates over the list and frees every single node in the list. This is actually not the correct thing to do, but I'll let it run and let you figure out why. All right, what do you think will happen when I run this? If I compile this and run it again, what do you think will happen? I'm just gonna compile it now before I. Correct. It will segfault. Uh, ta-da! It it actually aborted. It didn't segfault. It aborted. Because free was passed an invalid pointer. And why was free passed an invalid pointer? That's not correct. Um, all the code is correct. The only errors are in the main function. All of the implementation code is correct. It's how we're using the implementation code. No, we don't need to dereference anything. I already passed in a reference to the list. I'm not passing in the list itself. Okay, I'm gonna give you guys a few more seconds. I'll let you look at the implementation of destroy just so can you guys can see what's wrong. Okay, I'll I can't see the chat now, so I'll just let you guys look at it for now 5 seconds, and I'll see if anyone's answered. No? Okay. Never mind. The answer is here. We deallocated the list. We deallocated the pointer to the list. But if you see in our main function, we declared the list on the stack, right? So we tried to free an invalid pointer because the list is a stack variable, not a heap variable. You can only free heap variables. Yeah, it's in the stack. Exactly. So the correct thing to do instead of creating a list on the stack is you want to use this handy little function that I did. Linked list create. It returns a pointer to a linked list. It allocates the linked list on the stack. It checks, of course, if it checks, it returns null. Like I said, null is falsy, so this will evaluate to true. If null is false, then we just return null. So what we want to do, and it does everything for you as well. It initializes everything to 0. It clears up all dangling pointers. We're good. So instead of declaring a linked list on the stack, instead we do this. And now we have a pointer to a list instead of the list itself. And this means that we need to remove all these because now if we do this, we're giving a pointer to a pointer, and that's not correct. We just want a pointer to a list, and that's what list is. So just remove all of this. I can remove this now because there are no more problems. And of course, we need to set list to null because we are because we just destroyed it, we just freed it. So if we compile this again, we say that it runs correctly, and if we run valgrind on it, and we see that there were 9 unlocks, 9 frees, everything matches up, everything works. So, um, yes, we cannot free the list if it's in the stack, because, um, so so like I said, for every malloc there has to be 1 free. So if so in the previous case, our list variable was on the stack, but all our nodes were on the heap. So we have to free all the nodes instead of the stack. That's actually another thing, right? If you have a stack variable that points to a pointer on the heap, right? And a function returns, that stack variable gets lost. It vanishes. But that memory on the stack is still allocated, right? So now that is a memory leak. You have no way of freeing that memory because you don't have a pointer to that memory anymore. So, like I said, you need to check a lot of things in C. Yep, that's correct. The assembly code clears the stack. In order for me to talk about how call stacks work in C, it will require delving into assembly, and I do not have time for that. We are already over time. So, yep, that's essentially how C works. And like we said, as I showed you, Valgrind works. Valgrind returns everything. So this is the correct implementation of a linked list, or one of the correct implementations. Sorry, hold on. Okay, so homework. You guys don't have to do this. This is just if you're interested and want to learn more. Figure out how to do recursion. Figure out take my linked list and implement its operations recursively. Implement a Fibonacci number calculator recursively. You've done it in Python, you can do it in C. Implement the dynamic string read function I talked about earlier. Right? If we're reading in a string, we realize that we haven't read in enough data. We need to allocate more. Figure out the mechanics of it. I already given you how to do it. You just call realloc when needed. Implement a binary search tree that just follows naturally from what recursion is, because search trees are recursive. Implement, if you have a small project in Python or some other interpreted language, try implementing it in C. It might work. Do some reading. What I've covered today is just scratching the surface of what C can do. Not what C can do, what C is, right? The history of C is intertwined so tightly with the history of Unix and really the history of computing in general. Like in fact, this is actually very useful for those taking hacker culture in CCT. The history of Unix is very important. And it really does follow like the rise and fall of the open source movement. Unix is tied up very tightly with what that is. Read up on how a C program is compiled. So I won't go too deep into it, but basically C compilation follows a 4-stage process. And in this you will learn stuff that's taught in interpreters and in compilers and systems. Compilers, the compilers course. I forgot what the course code is. You also learn why import statements use file names and why they start with a hashtag. It's very, very, very interesting. How malloc and free work, right? We're just calling functions. We don't know how they work behind the scenes. Figure out how they work. There are whole articles on this. In fact, there are multiple implementations of malloc and free that are worth looking into. Then you have the book on C by Brian Kernighan. He was there when C was implemented. He is an old man now. I think he's like 80 something. He wrote this is the book on C. It was written very, very long ago. It's several editions old now, but it's worth a read. So that's your homework. Do it if you want to, or don't do it. Up to you. And so that brings me to the end of my workshop. We're slightly over time, but thank you so much for paying attention to me, to the ramblings of a madman who's crazy about C. And yep, thank you for attending. I will stay here for any other questions you guys may have. See you later. Oh, thanks, Hamza. Oh, thanks, Michael. If you guys have any questions, just ask away. So this window manager is a Qtile. I hate that it runs in Python, but you know, it's Python. It's so easy to configure. That's why I use it. Yeah, thank you. Enjoy the rest of your day. Enjoy your dinner. Yes, that's a very good question. So my extensions are yeah, it's just the standard Microsoft extension pack, C++, all these. It's just the standard Microsoft extensions. Yep, no worries. Yeah, no worries. It was fun to make. I'm a first year. I'm a first year, so I can't give you any tips, but just read lots of C, study hard. All this I learned on my own. I'm sorry. uh, yes. Thanks for the compliment. Right. If there are no more questions, I guess I can end the. If there are no more questions, any more questions? No one? All right. All right. That's the end of it then. Thanks for sticking around and enjoy the rest of your day.